start?
Yeah.
Okay. So thank you very much again for all of you for being here. I will try to explain to you some of the ideas I find interesting in this theory of maps between surfaces. So a while ago, when Ridi asked me for an illustration for the poster, I sent this picture here. Sorry, I sent this picture here. This is taken from an old book on biology, in fact, a very interesting book. A book which is rediscovered over and over again by scientists, in fact. It contains so many great ideas. I will give you the reference. It's in the next slide. The book was written in 1917. I first heard about this book by reading an article by René Thom. Some of you might have heard of him. This is a mathematician from the late century, 20th century, a great French mathematician who got the Fields Medal, in fact, mainly on his work on topology. But he also worked on biology, and he invented this theory, which you might have heard of, called catastrophe theory. It's a great theory. So he writes several times in his even mathematical papers that all these ideas I got from reading this book by Darcy Thompson. So let me tell you why I find this interesting. In fact, recently there was also there's a lecture, in fact, by John Milner, who is also a Fields medalist, a great mathematician, and you can find the registration of the lectures on YouTube. He gave a lecture at the Institute for Advanced Study in Princeton about this book, in fact, by Darcy Thompson. I will give you as I told you in the next slide, the reference. And finally, also recently there was a biologist, a great biologist in France, who has had the chair of biology at Collège de France, which is the most prestigious. It's more than a university in France. It's a university, but there are no registered students. Everybody can come and hear the lectures, and the greatest scientists are professors there. So his first lecture was precisely on this book by Darcy Thompson. So this is a map. This is supposed to suggest a map between this fish here and this fish here. The two fish are a priori very different, in fact. One of them, the size, this size is supposed, it's shown to be greater than this one, but in fact it's about 20 times greater this is a very big fish, the one to the right. It lives in the Indian Ocean. And the shapes are very different. This map, what is suggesting is a natural map between the two fish. The suggestion, you see, it's these small rectangles here are sent to topological rectangles, but curved rectangles. And it suggests several things, in fact. First of all, the map preserves, you see, people who who work in biology, there are several trends. In fact, it's not like mathematics. In biology, you have several schools of several theories. So one of the theories, this is evolution theory. So the question is whether there was some evolution, continuous evolution from this fish to this one here. So you have this fish, you have this one here. So was there at some point in history some fish which is intermediate between the two? And how would it be, and how can we guess how it is? So this so you want to have a family of maps, not only moving continuously from this fish to this fish, and you want the maps to I wrote it here, stratification preserving. So in the fish there are several strata. There are the wings, there are the eyes. You want the map to send the eye to the eye. You want it to send the mouse to the mouse. Of course, they may be there are other maps in terms of mathematics. There are other homeomorphisms between this fish and this fish. But you want in this biology theories, you want the maps for instance, to send this tail to this tail and so on. So this is called a stratification preserving homeomorphism. And by the way, René Thom, whom I mentioned, introduced the notion of stratification in stratified spaces in topology. And he writes, I learned the word stratification from this biology book. So this is just to tell you the importance of this map. So anyway, okay, as mathematicians, we do not, in principle, we do not care at all about biology or evolution or fish or anything like that. But we have a map from here, from this picture, in fact, to this picture. And a natural question is, okay, how can we measure the distortion of such a map? Of course, the map cannot preserve distances because, and even it cannot preserve distances up to scale because you see this distance is more or less the same as this, but the height here is very different from the height here. So the map cannot be a homotopy. It cannot preserve distances up to scale. So what is the question which a mathematician can ask? What is the best Lipschitz map between this between this figure to the left to this figure to the right? This is one of the main topics which I will talk about, best Lipschitz maps between surfaces. So now I want to go, yeah, okay, so this is also from the same book. Why did I get this? There's something below, maybe? Yeah, okay, thank you. Okay, thank you. So this is the title of the book. It's called On Growth and Form. It has been translated into French. I don't know what about Indian, but maybe someone from you, if you are interested, you can translate this book in Indian and publish it. I think it's a very important book. If there's no translation in Hindi, and since it's from 1917, there are no more any copyright. So, okay, so these are shells of crabs, and shells of different crabs. All of them have names. Usually the names are Latin names. They are written here, 2 small characters, but you don't need to read them. So all of them are crabs. And the same question, what is the best Lipschitz, mathematicians can ask, what is the best Lipschitz map from here to here? The map which has least least distortion, least metrical distortion. And among all these, this could be, I mean, this is very natural mathematical question. I talked, how do I go? How do I go from page to page?
This one.
Okay, thank you. Okay, so I mentioned geography. I mentioned geography before, and you have the same question. In fact, the main question for geography, or the part of geography which is concerned with building geographical maps. I mentioned Euler, and this is also Euler's concern about geography. Is well, you have a country. In principle, the Earth is considered as a sphere. You have a country drawn on the sphere, and you want to represent it on a piece of paper which is Euclidean. It has Euclidean geometry. A piece from spherical geometry to a piece of Euclidean geometry. What is the best way you can represent it? And the best way is the way which distorts less the distances. What is the best least distortion map from a piece of the sphere to a piece of the plane? So same kind of question. So now if I want to put this bigger, I want to remain on the same page, but make it bigger.
So from
here, okay. Okay, thank you. Yes, okay, very good. No, before. Yes, okay. No. Okay. Okay, so now I want to give the mathematics behind this, and mathematics we start with precise definitions, and this definition is was given by Thurston, another Fields medalist also, in a paper he wrote in 1985. So this is 40 years ago. I read that paper, and the paper is at the same time very difficult and very simple. It's very simple because you can read it. There's no reference to any theory. In fact, you don't need to know complicated theory. There are almost no references. There's no reference to another paper. It's self-contained. You can read it. It contains only basic mathematics, but it's a difficult paper because you have to imagine. You have to work by yourself. In fact, you cannot find. Today you can find references in other papers, but at that time it was very new. So it starts by the following definition. You have a surface S equipped with two hyperbolic metrics. I will talk about hyperbolic metrics later, but now, so these are metrics of negative curvature. The fact that they are metrics of negative curvature is not important now for what I will say. There are two surfaces equipped with metrics. You have two metric spaces, and the metric spaces are surfaces. And you have a map between them. So the map is between the same surface equipped with the first metric and the second surface equipped with the second metric. And then there's something which you call naturally the Lipschitz constant of this map. This is also a classical definition. What is Lipschitz? So in general, so you measure the distance between the images, the distance between the two images, and you divide by the distance between the 2 points. So in the images you use the second metric h. For the points you use the first metric g. So you have a map from SG to SH. And in general, you have I mean, all of you, I think, when you learned about metric spaces, you heard about Lipschitz. A Lipschitz map. A Lipschitz map is when the supremum over all pairs of points of this ratio here is bounded. If the supremum is bounded, then you say that the map is a Lipschitz map. And now, so this is the Lipschitz constant of phi. For instance, if the map is differentiable, since let's take compact surfaces here. Compact surfaces, I didn't say, but let's compact. If the map is differentiable, then the Lipschitz constant is always finite. This is a basic theorem. Okay, and now I want to define a distance between the two surfaces, the two hyperbolic surfaces, the two surfaces equipped with different metrics. And you say that the distance between these two surfaces, SG and SH, well, it is the infimum of this Lipschitz constant of phi, and you take the infimum over all possible maps phi. I said map phi homotopic to the identity. If you don't know about homotopy, don't worry about this. But you have two surfaces which are homeomorphic, since I said the same surface equipped with two different metrics, and you say that the Lipschitz map. You take only Lipschitz map, and you say that the distance between the two surfaces is the infimum of the Lipschitz constants of all maps between these two surfaces. So if you think about the picture we had at the beginning, you can ask the question, okay, what is the distance between the first fish and the second fish? And the map, which was suggested by the grid, will give you an idea of what is the best map between the two surfaces, and then you compute the Lipschitz constant of this best map, and this will be the distance between the two surfaces. So in conclusion, we are putting a distance function on spaces of surfaces. And in my title and in the summary of the course, I talked about Thurston distance, and the Thurston distance is exactly this distance between surfaces. You take the best Lipschitz map between them, and you well, you have to take logarithm for no. I mean, it's not very important, but you have to take the logarithm. The logarithm of this infimum here will be the distance between the two surfaces. So I said infimum over homeomorphism, homotopic to the identity. We don't care about this now. And so the Teichmüller space of S, which I will talk about, it's a space of all metrics on the surface, more or less. I will give a better definition later, but this is a space of all metrics on S, and then you get a metric. This space becomes a metric space because you are measuring distances between the surface S equipped with various metrics. So this makes this space of metrics itself a metric space, and this is the Teichmüller space equipped with the Thurston metric. So I talked about this paper of Thurston. It's this one here, 1985. It's called Minimal Lipschitz Maps Between Hyperbolic Surfaces. So now, from what I said, you understand more or less all these words here. It remained a preprint until recently, 2022, where it was printed in Thurston's collected works. But the preprint, you can find it on the internet. they published the preprint in the internet without any change. Yes, tell me please.
What if the leaf size is less than 1? Then, I mean, if you
this is a very good question, but this is special to hyperbolic geometry. The Lipschitz constant can never be less than 1. If the Lipschitz constant is equal to 1, this is one of the propositions, of the first propositions in this, because we are talking about hyperbolic metrics. I will explain several analogues of this Thurston metric on various spaces, in fact, and there will be spaces of Euclidean structures. But here you have to say something about the Euclidean structure so that this Lipschitz constant is never less than 1. This is a very good question. Yes, it's one of the propositions in Thurston's paper, one of the first propositions, that this Lipschitz constant is always greater or equal to 1.
Your best map is the minimal Lipschitz map?
My best map is what? Yes, minimal Lipschitz map. The minimal Lipschitz map is the best map which I talked about. Okay, so now okay, so this is second. No, this is the fourth page. So as I just suggested, there are many possible generalizations. So the theory of hyperbolic surfaces with boundary, this is something different, a different theory. So when you have a paper like this, then you ask, as a mathematician, you have many questions. Some of them are good questions. What happens if the surface has a boundary? It turns out that the theory for surfaces with boundary is different from the theory for surfaces without boundary. I will talk about this. And then surface with funnels, this is proper to hyperbolic geometry. I'll explain to you what are surfaces of funnel. Surfaces of infinite type, so in fact this is also some very natural setting for this kind of theory. Euclidean surfaces, surfaces equipped with Euclidean structure. So surprisingly, the theory for Euclidean surfaces, which is easier than the theory for hyperbolic surfaces, people started working on it very recently. In fact, they asked the right questions and they developed it. So here I think I gave some. So I gave mostly. I told you I wrote on this. I worked on this for 40 years with students and colleagues and so on. So I know more my work than the work of others because I understand it more easily. My papers. So these are recent. I'm just giving you a list of papers to tell you that this is a very living subject. In fact. So this is a paper 2025 called Minimal Stretch Mass Between Euclidean Triangles. So the surfaces, so I started with this complicated picture of fish. And then I talked about hyperbolic surfaces, but now if you take, if your surface is just a Euclidean triangle, so in other words, my space is the space of all triangles in the plane. And I want to put a metric on this space of triangles in the plane, and I want to study the properties of this metric. And there are a lot of very good questions on this space. For instance, let me come here. Let me come back here. You see, you are studying. You are studying. You want to study best maps between this fish and this fish, and okay, this is suggestive picture by a non-mathematician whose mathematical intuition is very, very profound intuition. So he said, okay, the best map between these fishes is probably this one with this grid, this rectangular grid transformed into this grid. And then I mentioned the name transformation, you know. So how do you pass? What is, if we believe that okay, nature takes always the simplest path, so this is a hypothesis, if there was, if evolution, a certain evolution theory which is I mean, interesting, this fish by an evolution became this fish. What are all the steps of this evolution? What is a natural, the most natural and the most energy minimizing path between this family of fish and this family of fish? So when I go here again to this paper on Euclidean triangles, so you may ask the same question, okay? So you put a distance on the space of triangles, which I talked about. It turns out that you have, I mean, it's interesting and important to consider only triangles of the same area. If you multiply the triangle by a constant, then you get you want to consider the triangle as similar to the first one. So this is a metric on between Euclidean triangles up to homotety. Okay. It turns out that this and you want to, so when you define a metric on this space of triangles, then there are very good questions. There are very good questions on this metric space. You can ask, for instance, can you describe geodesics for this metric? Meaning, can you describe shortest paths from going to one triangle to another triangle? It's a path constituted of a family of triangles, but it's shortest path among all the paths that I can draw between the two triangles. It turns out when you define a metric, a good question is to know whether this metric is a Riemannian metric. This is for mathematics students, because there are some, if you know a little bit of Riemannian geometry, is this metric given by an infinitesimal form, or and so on and so on. So we studied, this is first paper I wrote on this with a Turkish postdoc who came to work with me, and then it turns out that this theory works well for acute triangles. If you take all the triangles in the plane, including the non-acute triangles, then there are several questions which we don't know how to solve. So if you read this paper, and if you have ideas on, I mean, more general, on the space of more general triangles, this is very good. And then I have, then there are several other papers, and this is space of singular flat metrics. This is also on surfaces. So instead of the hyperbolic surfaces which Thurston started with, you can consider Euclidean metrics on a surface which is not a planar surface, but there's a theorem, there's a result in geometry, a basic result. If the surface is not the torus, you cannot put a Euclidean metric on it. But you can have Euclidean metrics with singularities. I will give examples later, I will give pictures. So, okay, so we said, okay, we want to consider surfaces of higher genus, not the torus, but with Euclidean singularities. With Euclidean metrics with singularities. So this is, it turns out you you can say a lot of things, and there are a lot of open questions on this. Everything we know, we put it in this paper, but there are a lot of other questions which we did not touch because we are only two persons and we cannot work more than 24 hours a day, and we need other people to work on this. So this is also still a living subject. So here is also. So I mentioned that some of the metrics which you define, some of the metrics on spaces of metrics, turns out to be not Riemannian metrics, something weaker, which is called Finsler metrics. So the Finsler metrics have they have infinitesimal descriptions, and this is a paper also with my with my Chinese colleague Yi Huang and my Japanese colleague Kenichi Oshika. We study the infinitesimal structure of this space of metrics. So these are examples of things which are done on this work. So I want to talk about Euclidean metrics, which is something more familiar to you. But I want to talk also about the hyperbolic case, which is the initial setting of which Thurston started with. For this, I'm trying to follow now the program of these lectures. I said I will talk a little bit about hyperbolic geometry, so that you know a little bit what is this hyperbolic setting. So probably many of you know a little bit. I mean, probably students in mathematics know a little bit about hyperbolic geometry. But I will give more later. But now I want to give just a little glimpse into this this theory, which I like very much. So I said that I read the Lobachevsky, and I wrote a book on his geometry, and I wrote also an article for Ganita Bharati on non-Euclidean geometry, which, if you are interested, you can. I mean, I'm not sure you can find it in the library here, because this journal is not. I mean, I think it's not very well known in India. I remember somebody told me, "Oh, I don't know this journal," a colleague of mine. Anyway, so they are. So let me say a few words of introduction today on hyperbolic geometry. So, okay, you know, people when they learn hyperbolic geometry, they start with models. I mean, you want to see what are the what are the lines for this geometry? So what is a geometry? In fact, to define a geometry, you have to define points and lines, and you start with this. Well, the lines means the straight lines. The straight lines in the Euclidean geometry. The straight lines in the Euclidean geometry are the shortest distance between points. In hyperbolic geometry, you have the straight lines, which are curved here, but they are straight lines of my geometry, which are the shortest path between 2 points. The straight lines, knowing the straight lines in a geometry means that you know everything, in fact, because the axioms of a geometry concern only points and lines. If you look at Euclid's axiom for Euclidean geometry, you have axioms between points and lines, and hyperbolic geometry is just a little modification of these axioms. And it has to do only with lines. Let me also tell you, as I said at the beginning, I read Lobachevsky, and in Lobachevsky there are no models. In fact, he was working he was doing all his work on hyperbolic geometry, which is a very profound works. In fact, he was computing areas, volumes of three-dimensional polyhedra in his geometry and so on. But he didn't know any of these models. So you don't need models. In fact, he was just thinking in terms of lines and axioms, and he developed the theory, which, I mean, the development of Lobachevsky is more or less what we know now about this geometry. When they discovered the Euclidean models here, they didn't prove almost anything more than what he knew.
He was working with the constant negative curvature, or?
Constant, yes, always, yes.
Not variable.
No, always constant. So when I'm talking now,
I'm talking about
Lobachevsky only constant negative curvature. Of course, he was not talking about curvature. He didn't have this notion of curvature. It came from Gauss after him. But he was proving all the theorems about this geometry with lines and intersections of lines, and it was abstract. It was concrete, in fact, is in mind, but without any model. So, but it's easier to work with models now, since you have these models came much later than they came 100 years after Lobachevsky. These models. Because we have formulas, you know, and I mean, most people like formulas. I cannot read formulas. In fact, I cannot work. I'm always embarrassed to say that formulas for me do not mean anything. I always think about using lines and I mean, not only in this theory, but in general. So anyway, the easiest, if I tell you, okay, here are the axioms of hyperbolic geometry, then after this, you tell me, okay, but what should I do with these axioms? But when you have the models, it's easier. So this is why I'm talking about models here. So there are two main models. This is the disk model, and this is the upper half model. And in these models, the lines of the geometry have a description in terms of Euclidean geometry. So, for instance, in this model, the lines are arcs of circles which are perpendicular to the boundary. Arcs of circles which are perpendicular to the boundary, all of these. So, for instance, this diameter of the circle is also considered as a circle perpendicular to the boundary. You see, this is a picture of a collection of lines in the hyperbolic space. So if you are a geometer, then you said, okay, so I don't find here any triangle, but usually geometers, I mean, as a geometer, I like to see triangles. I don't see any triangle. Somebody sees a triangle here? This is a this is a quadrilateral here. I can see a here is a small triangle. Here is a small triangle. You see this triangle? Okay, so I have a geometry with lines, and I have a triangle. A triangle is formed by three geodesics which intersect intersect pairwise. So, yes, thank you. There's another one here. Thank you. I have it here trying. So, okay, as a geometer, I say, okay, this is a new geometry. So, what would I do with this new geometry? And then you want to study properties of triangles. So, the first question is, okay, I have three triangles. So, I take what? I take the three altitudes of this triangle, and do they always meet in a single point, like in Euclidean geometry? The three perpendiculars. Yeah, I didn't tell you also that in this metric you can measure angles. You see, you can measure angles like in Euclidean geometry, and the angles are the same as the Euclidean angles for some obvious reason, but I don't want to talk about this now. So this angle is around I don't know, maybe 65 degrees and so on. So you take this triangle, you draw the three angle bisectors, and you want to see whether they intersect in the same point as in Euclidean geometry, which is not at all obvious because it's not Euclidean geometry. And then you try a little bit, and you see, well, yes, in the triangles I see that it's correct, and then you try to prove this. And this is a theorem, in fact, a proposition in hyperbolic geometry, that in any triangle, the three angle bisectors or the three altitudes meet at the same point. But it needs a proof. It doesn't follow at all from the Euclidean, from the same proposition in the Euclidean setting, right? So this is a new geometry, hyperbolic geometry, and so you have lines, you have angles, you have perpendiculars, and so on. And okay, this is another model. Another model. I don't see triangles here. I see quadrilaterals. So after, let's see. Yes. No. Where is this triangle? This arc.
Yeah.
Okay, and the second one is this one?
Yes, and the semicircle.
And the semicircle.
No,
No. Yes, you are right. But this is a triangle where the vertices are at infinity.
Oh, yeah.
This is very important, but it's not what I'm. It turns out that in hyperbolic geometry you have. You have a good notion of what is at infinity. Here the infinity is this circle. Here the infinity. It's called the boundary at infinity of your space. And you have also triangles where whose vertice is at infinity, and they are very important, in fact. And Lobachevsky, without having any model, he talked about triangles which have angles at infinity, and the angles are zero. But here I don't find any on. But anyway, you have quadrilaterals, you have hexagons, and so on and so on. So this is what you do with hyperbolic geometry. Like with any kind of geometry, you want to study properties of triangles, quadrilaterals, and so on. There are many theorems in Euclidean geometry about quadrilaterals, and then you want to know whether the same theorem holds for hyperbolic geometry. Not all the theorems hold. Some of the theorems fail. You see, like obviously, the theorem which tells you that the Euclidean theorem which tells you that the angles in a triangle is always 180 degrees. This theorem fails in hyperbolic geometry. And if you want to understand, then it's not difficult, in fact, but it's one of the basic theorems in hyperbolic geometry, which Lobachevsky proved without any model, that the sum of the angles is always strictly less than 180 degrees. Okay, so these are the two models, and there are formulas. There are formulas for distances, which I didn't copy here. There are formulas for which you can compute distances between points and lengths of paths and so on, which we will see a little bit about them later. And now I said also that I said that I want to talk also. I put in my in my outline that I want to talk also about the geometry of the sphere. For several reasons, in fact. I already mentioned one reason, this theory of Best-Lipschitz maps, where you consider the Earth as spherical, and then you have a country here, like India, say, and you want to build a map of India. And what is, I mean, how do you do? How do you build this map? You want a map to be best Lipschitz map, but also to preserve some other things which I will talk about when I will talk about geographical maps. This one, Euler has 3 long papers about this, and then other geometers, in fact, like Darboux, Chebyshev, and Lagrange. I mean, several people wrote papers called on the construction of geographical maps. Mathematicians, I'm talking about mathematicians. Of course, geographers, there are thousands of papers about how to construct geographical maps, but if you look a little bit, I mean, not interesting. Most of them not interesting at all. Well, the papers of the mathematicians, at least you know what he's talking about. There are definitions and there are metrics, and you're talking about. Whereas the geographers, it's always mixed with. I mean, they make measurements. You see, I said that you are considering the Earth as spherical, but it's known, in fact, since Newton, that the Earth is not really spherical. It has the shape of an ellipsoid. In fact, it's a little bit flattened at the pole. So so if I exaggerate, it's like this. It's more an ellipse of revolution. So it has. There's a rotational symmetry, but on the top and bottom it is flattened. I'm saying this because the people I mentioned, like Euler, they knew that the Earth was more ellipsoidal, and Euler wrote a paper which is not the 3 main papers I talked about, but another one on the geometry of the ellipsoid and how you measure distances on the ellipsoid, and properties of some triangles on the ellipsoid. He didn't know how to deal with all the triangles, but some of the triangles on the ellipsoid, mainly the triangles where one of the vertices is at the North Pole. I mean, at the North Pole, which is flat, where the surface is most flattened. So this is also something which is interesting, in fact. Everything I say about spherical geometry, if one wants to do the analog for the ellipsoid, then it's fine and it's interesting, I think. Euler started this, but I think nobody, I mean, no mathematician studied Best-Lipschitz maps from the ellipsoid to the plane after Euler. So okay, so here we have also on the sphere. So so I wrote here, you have a great circle, and these are small circles. So what is a circle here? A circle is just the intersection of the sphere with a plane. This is a fact of Euclidean geometry. When you intersect a sphere with a plane, you get a circle on the plane. So some of the planes pass through the origin, and others do not pass through the origin. If the plane of the circle passes through the origin, then it's called a great circle, because its radius is the biggest one, but it's also the great circles are the geodesics. The lines on the sphere, I told in the previous slide, I told you what are the lines in hyperbolic plane. The lines on the sphere are the great circles. The small circles are not lines. You see, when you take when you fly with an airplane from here, say from whatever, from here should maybe Helsinki to St. Petersburg, no, St. Petersburg is too close. From 2 points which are here and here, the shortest path is not at all this one here. This would be very long. The shortest path should be something like that. So for instance, to go from here to here, the shortest path is this one. This small circle is not at all the shortest path. So in spherical geometry, you have the lines are the great circles. So for instance, here, this is only great circles. You take 3 great circles. You have a triangle.
Segment of great circle, right? Segments of great.
Yeah, you are. Yeah. Well, no. Here I drew the three circles. You are right. The three great circles are the lines. No, they are called the lines. The segments of the segments of these lines, yes, you are right, are the shortest path between points. To find the distance, to compute the distance between this point and this point, one way is the length of this segment of great circle joining them. This is what you're saying, right? In fact, there are 2 segments. One is this one here, and one is this one here. But you must take the shortest one between the two, the shortest length. So anyway, so you have spherical triangles, and you have angles. It turns out that the angles. First, you must ask the question: what is an angle? In fact, I have a geometry with points and lines. So how do I get angles? Well, what do angles mean? So you come back to Euclid. Euclid defines lines and points. He never defines angles, but he works with angles. And how does he get angles? This is a very good question, in fact. I invite you to think about this. Okay, so here I'm telling you that the angles, you get angles on the sphere, angles between lines, and the angles are the same as in Euclidean geometry, which is not obvious, but you measure them in the same way. And for a triangle, you have 3 angles, and the sum of the 3 angles is always greater than 2 pi. This is a theorem also. I said that in Euclidean, in hyperbolic geometry, the sum is strictly less than 2 pi. Here the sum is always strictly greater than 2 pi. And then first, when you study this, the first thing, you want to know whether the elementary properties of Euclidean triangles are true in hyperbolic geometry. For instance, if I take a spherical triangle and I take the 3 perpendiculars from the sides to from the vertices to the sides, do they meet? Do they always meet in a single point? The answer is no. In fact, in spherical geometry, it doesn't always work, but there are conditions. In fact, so let me tell you one. So okay, let's take. So every one of you, I'm sure, who heard about the sphere and the geometry of the sphere, you know that the sphere has you have triangles with 3 right angles, right? So here is one. Here is one segment of great circle here, and then take the one perpendicular to it that starts here, which is perpendicular also to the equator, and this is a piece of the equator, which is so this. Consider this spherical triangle with 3 right angles. Okay, and now I want to study. I want to answer my question about the 3 altitudes meeting in a unique point. So for this triangle, okay, I start from this point. Well, since this is perpendicular to the other side, this is an altitude, right? This is also an altitude because it's perpendicular. It goes from one vertex to perpendicular to the other side, and this is also an altitude. The sides are altitude, and they don't meet in one point, right? And I can take more complicated examples. I don't need this triangle with 3 right angles. It turns out that in spherical geometry, you have this theorem which tells you that if each of the 3 angles is less than a right angle, then the 3 altitudes meet in one point. So this is just an example to tell you that okay, this in spherical geometry you have also lines and triangles and so on. Some of the theorems of Euclidean geometry hold, some of them do not hold, some of them hold with some extra conditions like the one I just said. And you need to know about this when you want to study, and I will give you examples, when you want to study best Lipschitz maps from a surface to the other, from a hyperbolic surface to a hyperbolic surface, or from a spherical to spherical. You need to know a little bit about these theorems of non-Euclidean geometry. If you don't know them in advance, then you learn them at the same time. And I have my next slide here. I talked about hyperbolic geometry a little bit. I talked about Euclidean geometry a little bit. I talked about spherical geometry a little bit. So let me mention something in which I'm interested, and I wrote a few papers on this. I learned this with a colleague of mine in Basel. His name is Norbert Acampo. So there's a geometry which he gave it the name transition geometry, in fact, where you pass continuously from Euclidean to from hyperbolic, say, to Euclidean and then to spherical, continuous paths. And then you ask, okay, what are the theorems of one of these geometries, say Euclidean geometry, because you are more used to it, where you can pass continuously from one geometry to the other, and what happens in this continuous deformation. So somebody asked me here if the curvature is constant, negative, constant, or variable. We are talking about always constant curvature. But we are varying the geometry continuously. So what happens to the trigonometric formulas when we pass continuously from one geometry to the other? What happens, I mean, how do you, what happens to the geometry of the triangles, and so on and so on. So this is one other thing which I will not have time to talk about. But there is this question of transition between the 3 geometries. And this is why I like to talk about them together, in fact, the 3 geometries at the same time. So now this is something on spherical geometry, which is related to the problem I mentioned, the problem of finding best maps, best geographical maps. So we start with this proposition. Let's start with this one here, the second one. So I take a spherical triangle, ABC. I take D, the midpoint of this line AB, of this side AB, and E, the midpoint of this side BC, and I join them by a shortest arc, a geodesic, and then the theorems. The theorem in spherical geometry tells you that DE is strictly less than AC. in Euclidean geometry, if I take a triangle, Euclidean triangle, and then I take the line joining the middle, the midpoints, then I take an equality that DE is equal to half of AC, right? In spherical geometry, there's a strict inequality. I mean, whatever triangle you say, big, small, angles, and so on, it's always greater. Why I'm talking about this now? I'm talking about this because it implies this first proposition here. This is a proposition which I mentioned before, that there is no map from a region of the sphere to the Euclidean plane which preserves distances up to scale. It means, in fact, that you cannot construct a geographic map where the scale is the same everywhere, right? It's just because suppose I want to make a map of India, then I take a triangle, the shortest lines between Bombay, Delhi, and Calcutta. This is a triangle. So I want to, on my map, I want these three distances. I want these three distances to be of the same scale on my map, right? Let's say 1 over 1,000. Okay, 1 over 10,000 or 1 over. But then I will always find, by taking the midpoint of this triangle, I will always find 2 points where the distance on the sphere compared to the distance on the plane will not be 1 over 10,000 or 100,000, right? So it means that there are no good geographical maps. There are no geographical maps which are where there is a similarity, yes. So when on a geographical map you find here 1 over 10,000, this is always a lie. In fact, it's not possible. And this is why geographers and mathematicians then say, okay, so what do we do with this? People need geographical maps. How do we deal with this? So they always try to find maps which are methods of constructing geographical maps which almost preserve the distances up to scale. So what does it mean, almost? And this is where you have to work, in fact, and this is where Euler described in his papers methods of constructing geographical maps, and he proved that okay, these are better than the ones we know, and so on and so on. So this is and this business of finding best geographical maps, it's the same question as finding best Lipschitz maps between surfaces. So we were talking about best Lipschitz maps between hyperbolic surfaces or between Euclidean surfaces and so on. Now if I mix the geometries, I have a geometry of positive curvature, the sphere, and then a geometry of the plane, the question is how do I find best Lipschitz maps from parts of the between triangles, say. We forget about maps of complicated maps of countries just between triangles. What is the best Lipschitz map between a spherical triangle and Euclidean triangle? Can I find a method? And does this method depend on the angles of the spherical triangles, if it has very, very large angles or very small angles, and so on? So this is part of what of the questions that are interesting in this theory. Okay, so now we come back to the original question by Thurston. So I wrote here. Okay, so I want to talk about ideal triangles. And Thurston's Thurston's construction of Best-Lipschitz maps, the basic element, in fact, in this theory is the question this figure of an ideal triangle. So this is not an ideal triangle. An ideal triangle is here, and I will talk later about it. But first, I want to say something about the other. So this is a triangle where the three vertices are at infinity. This is an ideal triangle. This is an ideal triangle. This is an ideal triangle. I mean, all of these are ideal triangles. You see, I said I want to give an idea of hyperbolic geometry. So one of the basic things of hyperbolic geometry is the existence of these ideal triangles. Ideal triangles that is vertices are at infinity, and the angle at the vertices is 0. I talked about Lobachevsky at the beginning. Lobachevsky works with ideal triangles. In fact, he didn't have any model, but he understood and he knew that this very important ingredient in hyperbolic geometry, that you have triangles with where the angles are 0 and when the vertices are at infinity. And they play a major role in Thurston's theory. So another thing you have to know about ideal triangles is that this one and this one and this one, they are all isometric. What does it mean that they are isometric? It means that you have an isometry of the hyperbolic plane, an isometry of the whole space, which takes one triangle to another triangle. So there's an isometry which there's a rigid motion of this hyperbolic plane, which takes any for any pair of ideal triangles, there's a rigid motion of the space which takes this one to this one. How can you? I mean, there are. If you write, there are ways of doing this in models, but something which is true in hyperbolic geometry, and which is also true in spherical geometry, is that for a triangle, let's see here. No. Okay. Let's start with here. I wrote this proposition here. Good. So this is a triangle with 3 edges and 3 angles. The isometry type of this triangle is determined by this is very easy. This is like in Euclidean geometry. This is not what I meant when I wrote this, I will tell you. So if I give you 3 in Euclidean geometry, if I give you 3 numbers which satisfy the triangle inequality, the 3 triangle inequality, then you have a Euclidean triangle with these 3 edges, right? And this triangle is unique. This is true also. This is what I'm saying here. This proposition it's not difficult to see, and it's not surprising that the 3 edges determine the triangle up to an isometry. The thing which is special to yes, you're right. Now I'm talking about, this is a second mistake here. This is hyperbolic. So I meant the proposition for the hyperbolic. It's also true in spherical, but I'm talking about hyperbolic. It's determined by the three edge lengths. But my first mistake, what I want to say here is that it's determined by the angles. The angles in hyperbolic and in spherical geometry, the angles determine the sides. If you give if two hyperbolic triangles have the same angles, then they are isometric. I will give you some trigonometric formulas, in fact, next time, which gives a precise, this is a precise formula for the edges of the triangle in terms of the three angles. Yes?
Edge length thing is wrong also.
Excuse me?
Edge length is wrong also.
Edge lengths, yeah, it's true also for edge lengths, but
Hyperbolic triangles are also determined by
are also determined by the edge lengths, but they are also determined by the angles. Angles, they are also determined by the angles, and this is what I meant here.
But in Euclidean geometry, the angles don't determine
Exact. In Euclidean geometry, this is not
the
correct.
scale. Yeah.
Yes, right. Right. In Euclidean geometry, the edges, the angles do not determine the triangle, but in hyperbolic and Euclidean they determine. And why did I say this? I said this because, okay, I was looking at this picture. I said that all these triangles are isometric. In fact, not only they are isometric, but there's an isometry of the whole space, which sends one of these triangles to the other triangle. There's a rigid motion of the space, which sends any one of these, because they are all isometric, because they have zero angles, and I just told you that the angles determine the sides. So zero angles is fine, and okay, this is very. I mean, this is a very important property of these triangles, which are ideal triangles. And now the construction. I said that one of the themes here is the construction of best Lipschitz maps. So Thurston's theory starts with the construction of Lipschitz maps from a triangle, from an ideal triangle to an ideal triangle. This picture is taken from Thurston's paper. So okay, so this is an ideal triangle, a triangle with three zero angles. The lengths of the sides are infinite. So it's also the fact that the sides determine the triangle. I have three infinite sides, so there's only one ideal triangle. Since the sides are equal, three of them are infinity. So okay, so now and this is an important ingredient in this theory. This is a very important ingredient. I should have made another picture, but it's fine. So suppose this triangle is sitting in the hyperbolic disk. Okay. So now these pieces here of circles, this is special to Euclidean hyperbolic geometry. You have lines which are called horocycles. The horocycles in the hyperbolic plane are the Euclidean. In this model, they are the Euclidean circles which are tangent to the boundary. Okay, so imagine here these pieces, all these pieces of horocycles are pieces of circles in the hyperbolic space which are tangent to the boundary. Tangent, I mean tangent from the Euclidean in the Euclidean sense. They make zero angle with the boundary circle, with the boundary at infinity of the space. Okay, and you have to imagine that there's you see you start taking a small horocycle, then you make it bigger and bigger and bigger and bigger and bigger and bigger, and you do this at the same time from the three sides. You do this at the same time, the same same velocity of making it bigger and bigger. So it's more or less clear that these circles will, there is some point, because of the symmetry, there is some point there are 3 points on the sides where you cannot make it bigger. Okay, so this is called the horocyclic foliation of the ideal triangle. And since, as I said before, there's only one ideal triangle up to isometry. So, for instance, this one here, which is the most symmetric one, when I draw it in this Euclidean model. So you start here more and more and more from these sides. So there's a unique on each side there's a unique point where you stop. This here and this one here and this one here. So this figure will be valid for any ideal triangle, since they are all the same. They are all isometric. There's no difference between one or the other. There's a rigid motion of the space which takes me any ideal triangle to the other. So, okay, so I get these fields of lines here. The 3 fields of lines are called a foliation. So a foliation is just a set. A foliation is just a set of lines like this, like a vector field, but without orientation. You know what is a vector field, right? So a foliation is just a vector field with no orientation. So you have this foliation. You have this foliation which do not cover the whole Euclidean, the whole. Well, here it's a hyperbolic triangle. It covers it except for a small region here, and it's a foliation by horocycles, pieces of horocycles. Okay. Now, the map that Thurston defines is, this is distance t, hyperbolic distance from this distinguished point. There are 3 distinguished points on the boundary. I want to send this piece of horocycle to a horocycle which is at distance k times t. So the first one is fixed because k times 0 is 0. The first one is fixed, but this one here at some positive distance t is taken to this one, and so on. So this defines, this tells me where I send each horocycle, each piece of horocycle, and then I make the map. So on each horocycle, I make it just distance preserving up to scale. So I told you now where each horocycle goes, and I told you on each horocycle what is the image of each point, since this length must be going from this piece of horocycle to this piece of horocycle. It's I take the most obvious linear map.
So here angle dividers meet at one.
I don't. There are no angles here. I mean, the angles these are always perpendicular. Perpendicular, yeah, they are perpendicular because.
Dividers meet at.
What dividers?
Those lines.
The dotted line.
Ah, yes, the dotted lines. I'm not using them, but what do you want to do with this? Yeah, they are preserved. They are preserved. Yes, it sends the middle to the middle. Yes, it sends the middle point to the middle point. You are right. You are right.
That means in only hyperbolic and Euclidean, not spherical.
In Euclidean, this and spherical, you cannot do such things because you don't have horocycles. So you have to invent something else, and you don't have ideal triangles also. So this is why the Euclidean theory is completely different, and the spherical theory also is different. This construction is the most basic construction in this paper of Thurston, of which I gave you the reference. Yes.
Giving definition of a elliptic map.
Yes.
In a particular case.
Yes.
So far, you have not defined it in general.
No, only in this particular case. And I'm saying that this construction here is the basic construction in Thurston's paper, because I want to just to yeah, I have this picture here, this picture here. This picture also is taken from Thurston's paper. So you see so here it's not very clear, but here you see this. There is each time you see something like this, a small triangle. This is the central triangle of an ideal triangle. So one basic fact of hyperbolic geometry. This is a surface. This is a surface without boundary of genus 2. You can cover any surface by a union of ideal triangles. So the ideal triangles, you see here it becomes thinner and thinner, and it wraps around. It wraps around infinitely. I mean, it goes. I mean, one of the basic things to understand about the hyperbolic geometry is to see how can you divide a surface? How can you divide a surface into a union of Euclidean of hyperbolic ideal triangles?
Finitely many.
Finitely many, because
So it's
it's a
a compact surface.
compact surface, and each Euclidean, each ideal triangle has a definite area, which is the area of one of them, of any one of them, since they are all isometric, and so they must add up to make the area of the surface.
So you are partitioning the surface.
Yes, I am partitioning the surface into these ideal triangles. So this may be easier here. This is a surface. This is a picture which which I made. It's not from. So you see there are many ways of partitioning the surface. There are many ways of partitioning the surface. For instance, okay, you see this is a surface which is a sphere with 3 holes. And if I take now look only on the topology. If I glue 2 of them, I get like above a surface with no boundary and with 2 holes like this, a surface of genus 2. Okay. So now this one, maybe it's easier to see. So this is also. Of course, this is only symbolic. I mean, you just to see how how the ideal triangles wrap around this boundary. So they are big. One of them is here. You can see the thick part in front of you. The other one is on the other side of the surface. And the sides they spiral along the boundary component, which is a geodesic. This is also part of the theory of hyperbolic surfaces. Any hyperbolic surface, if I take one closed geodesic here, one closed geodesic here, and one closed geodesic here, and if I cut the surface along these closed geodesics, I get 2 surfaces homomorphic to this one with geodesic boundary, and each one I can geometrically, each one is the union of 2 ideal triangles which spiral along the boundary. You don't need to know much about hyperbolic geometry, but this is one of the basic things that you have to know when you and it's always used in this theory, that okay, any surface, any hyperbolic surface, any hyperbolic surface can be divided into a union of hyperbolic ideal triangles. Yes, please.
Does it mean that all these surfaces you are taking as a quotient of the upper half plane by isometric group of that styling?
Yes, exact.
Gamma 2?
Exact. Yes. Because when you take the universal cover of this, you get all these ideal triangles like this one here. Yes, these ideal triangles which you draw here, they are covered by genuine ideal triangles in the universal covering. So Professor Shah will give something about universal coverings. You talk about universal and so on. So this is okay. So just I have to conclude now. So the basic thing about Thurston's theory is that this map here, between ideal triangles, it has a meaning when the surface is decomposed into ideal triangles, and it is the model of his best Lipschitz map. This is a best Lipschitz map. This Lipschitz map between ideal triangles, or a Lipschitz map from one ideal triangle to another, is the model, the absolute model for this best Lipschitz maps between the hyperbolic surfaces.
In this particular example, the map is defined from where to where?
The map is defined from this ideal triangle to itself, but it could be also defined from one ideal triangle to another one. Yes. And here, maybe I didn't say, it's the identity on this central. So this is why, let me end with this. This is why this map, this Thurston map, which is the best Lipschitz map between hyperbolic surface, I mean, it cannot be used as a map for in geography, because for geography, you want the map to be, when I tell you that this map is best Lipschitz, in fact, in hyperbolic geometry, here it's the identity. So I can make it a little bit better if I want the Lipschitz constant to be constant everywhere. And this is what we want in geography. You want the distortion of the distances to be the same everywhere. You want it to be equally distributed everywhere, in fact. This is why in geography, I mean, the problems are the same, but what you want is something different. And I will talk about this. I think one of the days I have announced a lecture on geography. Okay. Yes? Huh?
What was the main statement for this?
For this one, okay, you are right. In fact, the main statement is just a heuristic statement, which says that Thurston's best Lipschitz maps, of which I talked about in the definition, are like this. They are maps between ideal triangles, which when you glue them together, they give you best Lipschitz maps between surfaces.
Let's thank Professor Ratana.
Thank you.
And,
Thank you.